So welcome to another NST video. Today we're going to explore entropy and spontaneity. We're also going to cover Gibbs free energy, which will require us to make links between enthalpy and entropy. So before we move on, I recommend you to first watch Tahir's video on enthalpy on the same channel, and its link is in the description below. So now let's see what entropy is. So entropy is defined as the measure of the distribution of available energy among the particles in a closed system. We can also look at it as a measure of disorder in a substance in the microscopic state. Ordered particles like atoms in iron have a lower entropy than disordered particles like nitrogen molecules in air. We see that entropy changes as the state or the phase of a substance changes, because a solid phase has more regularly ordered particles. Liquid phase has relatively less organized particles, and a gas phase has the least organized ones. So we can see in this picture there's a system where the time progresses and the entropy increases. So this picture represents low entropy. This picture represents high entropy as there's more disorder. Quantitatively, entropy is equal to the Boltzmann constant times the natural log of the number of microscopic states possible. But for now, just remember that entropy is the measure of distribution of available energy among particles, and therefore how disordered the particles are. For now, you would just need to know the standard molar entropy values, which we will see shortly. Now let's do a question. State whether you would expect the entropy to increase or decrease in each state change with reasons. So we see that from a solid to liquid, there should be an increase in entropy, because we saw that a solid has more organized particles than a liquid. So there's an increase in S. Similarly, for a liquid to gas, there is an increase because liquid's particles are more organized than gas particles. Gas to solid is a decrease because you're going from a less ordered state to a more ordered state. Again, from gas to liquid is also a decrease. From solid to gas is an increase, since it's going from a highly ordered state to not at all ordered. So coming to absolute entropy. So this is a pre-calculated entropy value for a pure substance at a particular temperature and pressure. We also have a special symbol for the standard absolute molar entropy measure for substances, which are kept at a temperature of 273 K and a pressure of 1 atmosphere or 10 to the power 5 pascals, and it is called the S bar. So these are some values for the standard molar entropy for substances at standard temperature and pressure. Notice that as the state tends towards the solid, the entropy decreases as the solid state is more ordered. We see that in the gas state, the entropy is quite high, whereas in the liquid state, it's average. Whereas in the solid phase, it's the lowest entropy because it's the most ordered phase. Now let's see how can we calculate the entropy change that takes place when a reaction occurs. So this is the equation for calculating the change in entropy. Delta S is sum of the entropy of products minus the sum of entropy of reactants. So given that we have this reaction over here, our entropy change will simply be the entropy of C plus the entropy of D in brackets minus the entropy of A plus the entropy of B in brackets. Now let's apply this equation and find the change in the standard molar entropy of a reaction. By referring to this data in the table, calculate the standard molar entropy change delta S bar for the following reaction. C2H4 plus H2 gives C2H6. Okay, so we have the substance and the standard molar entropy here. So we can write down the formula again like this. We then just substitute the sum of the entropies of products. So we substitute 230 over here, and that's our only product. So we subtract the reactants entropy. So entropy of ethene is 220 and entropy of hydrogen is 131. So we add them up and subtract it from 230, and we get this as the answer, minus 121 joule per Kelvin per mole. Now you might have questioned, how are endothermic reactions possible since they produce energetically unstable products from energetically stable reactants? To answer that, firstly we need to see that this law always holds true. Next, we can write the change in entropy of the surroundings as a negative enthalpy change of the reaction divided by the Kelvin temperature of the reaction. Now, the endothermic reaction can occur because it is still spontaneous in nature. A spontaneous reaction favors the formation of products over the reactants and depends on various factors such as the enthalpy change of the reaction, entropy change of the reaction, and the temperature of the reaction. So, now an endothermic reaction can still be spontaneous if there is always an increase in entropy of the system that is greater than the decrease in the entropy of the surroundings. So if we have an endothermic reaction, the delta H is going to be positive, so this term will be negative. So for this to be greater than 0, this term, the delta S bar, that needs to be larger than this and positive. So we can see that for endothermic reactions, if the change in the entropy of the system is positive and larger than this, then we can actually have a spontaneous reaction that is endothermic, and thus that reaction will take place. Now, exothermic reactions can also be spontaneous given that the increase in the entropy of the surroundings, this right over here, we have just substituted this for this. So if this term is positive and greater than the decrease in entropy of the system, then the exothermic reaction will be spontaneous as well. Now you'll see this very famous endothermic reaction being done in many chemistry labs. Here you react these two compounds in a beaker, hydrated barium hydroxide and ammonium sulfocyanate. There's a drop of water under this beaker. So as you stir the reactants, it takes in energy and it freezes the water, so the beaker gets freezes to the dish over here. So now this reaction, it has a positive change in enthalpy, which means it takes in heat, but it is still spontaneous because the entropy change of the surroundings is negative but smaller than the amount of heat that it takes in to increase the entropy of the system. If we take the system and the surrounding entropy equation and multiply both sides by the temperature T, we get this, and if we again multiply by -1, we end up with this equation, minus T delta S is equal to delta H minus T delta S. Now this quantity minus T delta S is called the Gibbs free energy, more specifically Gibbs free energy change for the reaction. So now, since this was the condition for the reaction to be spontaneous, the new condition for the reaction to be spontaneous is this, delta G, which is this term, we call it the Gibbs free energy change now. So delta G is equal to delta H bar minus T delta S bar, and that should be less than 0. So we can shorten this up like this, delta G is equal to delta H bar minus T delta S bar is less than 0. So now this is the Gibbs free energy condition for a reaction to be spontaneous. Explain why the boiling point of water occurs at a high temperature of around 373 Kelvin. So we see that the enthalpy change when water converts its phase, or when it transitions into the steam phase, the delta H of that reaction, right, from H2O liquid to H2O gas is going to be positive since it's endothermic. And similarly, the delta S for this reaction, which is the entropy change, is also going to be positive, as we are converting a liquid into a gas, so we get a more disordered state from a more ordered state. So by comparing it with this equation, we see that delta H is positive and delta S is also positive. So for this to be spontaneous, now the T delta S term should completely eliminate and exceed the delta H bar term. So for that, the T needs to be very high. Only then will it sort of dig into the delta H and will actually become a value that's less than 0. So that's why it occurs at a relatively high temperature. Part B. So we want a reaction that is not spontaneous at high temperatures but is spontaneous at low temperatures. If it has to be spontaneous at low temperatures, then well, then the delta H has to be negative, because at low temperatures the Gibbs free energy is approximately equal to the delta H bar, as this term becomes negligible because of the small temperature. So that means overall the delta H must be negative for this. And we also have another condition, which is that it should be non-spontaneous at high temperatures. So if this temperature is high, then it is positive. So that should happen. So when will this be positive given that delta H is negative? Well, that can only happen when the delta S itself is negative, because then the negative T will multiply with negative delta S, and if this term is large enough, large and positive, it will cancel out the delta H, which is small and negative compared to it. So that leaves us with the answer that delta H is negative and delta S is also negative. Part C. Calculate the change in Gibbs free energy for the reaction calcium carbonate gives calcium oxide plus carbon dioxide using this table. So we are given with the standard molar entropies and the heat of formation of each of these compounds. We need to find the change in entropy of this reaction and also the change in enthalpy of this reaction. Only then can we use this equation to find the Gibbs free energy change. So firstly, we find the delta H bar. Similarly, we calculate the change in entropy using the same formula. We end up with plus 160.8 joule per Kelvin per mole. Now we can substitute these two values in this equation to get our answer. Delta G is equal to delta H minus T delta S. So delta G is equal to plus 178, which is our delta H, minus 298, which is the STP temperature, times 160.8 times 10 to the power of minus 3. So taking this difference, we get this, which is our answer. The change in Gibbs free energy is plus 130 kilojoule per mole.